Ladies and gentlemen, please welcome with a loud round of applause, Avinash Sodani, Chief Architect, Intel Corporation.
Thank you very much. Let me jump right into it. What I want to do is talk about the Knights Landing architecture, which is our next Xeon Phi processor. I will spend most of my talking about that, and then give you some flavor of some of the trends that I see from my side as things from the processor point of view, which actually pretty much matches what we have talked, what we have heard from the variety of talks today morning. So let me jump into this. So Knights Landing processor, this is the second generation processor, many-core processor targeted at HPC. It's the follow-on to Knights Corner, the first Xeon Phi processor. There are many innovations that we are bringing with this processor. There's several of these. We'll spend some time talking about those, but first and foremost of that is that with Knights Landing, with this processor, Xeon Phi becomes a self-boot processor. It's not an accelerator anymore with this. It is a processor in its own right. It can boot a standard OS. It becomes a standard IA processor. That means it's binary compatible. And then, just like a regular Xeon processor would. On top of that, we improved the scalar and the vector performance significantly from the prior generation. We actually introduced a very innovative memory architecture. We integrate memory onto the package, and it's a very innovative memory architecture, which we will spend some time talking about. And we also integrate fabric on this processor. So there's a list of big changes that we do to provide performance at a very power-efficient manner. It will be available in 3 different products. One is, which I just mentioned, it's a standard cell boot processor, which is the baseline. Then there'll be another product which will have the fabric integrated into that. And then the third one will still be the PCI card, just like a current Xeon Phi processor, co-processor, as a follow-on to that. But the main thing that we are focusing on is the first one, which is the self-boot one, and that's where I'll focus my talk. Right? Most of the thing we'll talk about is for the first one. So let me go to the next slide. So this gives you an overview of the Xeon Phi processor, the top-level architecture for that. So it's a tile-based, it's a many-core processor. We have a concept of a tile, and we have then many copies of that tile that sort of makes it a many-core processor. Each tile is what is shown on the right-hand side top there. Each tile has 2 cores in it. Each core has 2 vector processing units in it. Right? This is, on the current Xeon Phi Knights Corner, each core has 1 vector processing unit. So here for each core, you have 2 vector processing units. And then between those 2 cores, you have a 1 megabyte of shared L2. Okay? So that's what composes a tile. There's the box called CHA. I'll talk about that in the next slide. So it'll be clear what that box does. But that composes the tile. And now that tile is arrayed on the chip. There are 36 of these active tiles on this chip, and that gives you the full Xeon Phi processor. Now, in terms of memory, we have this high bandwidth memory called MCDRAM. Those are those 8 boxes you see around that. Each of those boxes is 2 gigabyte in capacity. So total, that's 16 gigabyte. And the aggregate bandwidth from that 16 gigabyte memory, 16 gigabyte is a big capacity in itself. So aggregate bandwidth from that is 400 plus gigabytes a second. So that's the amount of bandwidth you can get from 16 gigabyte of memory, which is on package. And in addition to that, we have 6 channels of DDR, which can support 1 DIMM per channel. And that 6 channels of DDR can go up to huge capacity of 384 gigabytes. So it's going to be like really big machine. And then the bandwidth from those 6 channels is 90 gigabytes a second. So you have like 90 gigabytes coming from this DDR, which is like up to 300 plus gigabytes of capacity. And then you have 400 plus coming from the 16 gigabyte of this. And we'll talk about the motivation for why we did it and all that just in a few slides. So you get an idea of why we got to this point. This is a one socket system, so there is no QPI. So it's unlike Xeon, there's no two, this is it, this is the one socket you have. Uh, we have fabric integrated on it. It's not shown on this picture, but that's also on the package. You have a fabric chip, just like you have those MCD RAMs on package. You have a fabric on the package as well. So that's what, but it's not shown here. In terms of performance, the vector performance, the peak is 3 teraflops, 3 plus teraflops of dual precision, and 6 plus teraflops of single precision. So it's like a humongous amount of performance in this thing. And the scalar performance, that means like if you were to run like one thread on this one, compared to running that on Knight's Corner, that's 3 times faster. So 3x improvement in the scalar performance of the. And if you compare with the Xeons, for example, in this time frame, this will be around a third to 0.4, so 0.3 to 0.4 of the Xeon in the time frame, which actually starts getting to a pretty respectable performance. In fact, if you look back, I mean, if you know Intel's processors, if you start talking about 0.3 to 0.4 of today's Xeon, that will be actually close to the processor that was just before Nehalem, which was in our laptops not that long ago. So it's actually a pretty decent single thread performance. I think that's it. That was my last slide. I think summary is what I just spoke. I think we'll probably do questions later, but that's it. I'm done. Thank you.